Welcome to the deep dive. Today we're tackling something that, trips up a lot of people working with Red Hat Enterprise Linux. That invisible wall, security-enhanced Linux, or SELinux. For so many sysadmins, it's this critical security piece, but also, frankly, a source of constant headaches.
Yeah, that's totally fair. And it's often frustrating because SELinux really forces you to kind of rethink how you approach system security altogether.
Right.
So our mission today, especially if you're maybe studying for your RHCSA, is to really help you get your head around it. We want to shift SELinux from being this obstacle to, more like a predictable diagnostic tool you can actually use.
Okay, I like that framing. So let's start right at the beginning. What is SELinux, fundamentally? Why is it so central to RHEL?
Okay, so it's what we call a mandatory access control system. MAC for short.
MAC, right.
Yeah.
Not like the permissions we usually deal with.
Exactly. Traditional Linux permissions, that's discretionary access control, or DSC. It's flexible based on users and groups. SELinux, though, it's rigid. It's baked right into the Linux kernel itself.
Baked in.
Yeah, deep down. It acts like this ultimate security gatekeeper for, everything a process tries to do.
Yeah.
It's a much, much deeper layer of security than just standard file permissions could ever give you.
That makes sense. Now, the origin story is pretty interesting too, right? It wasn't purely a Red Hat thing initially. It came from somewhere else.
That's right, yeah. A lot of people don't realize it started with the U.S. National Security Agency, the NSA.
The NSA, really?
Yep. They were working on ways to implement really strict mandatory access control on Linux systems. The goal was basically enforcing very strong information separation.
Okay.
They released it as open source back in 2000, and Red Hat saw the potential, the huge security value, and they really championed it. They integrated it into RHEL4, which was around 2005.
2005, wow.
And it's been enabled by default in RHEL ever since.
Now, that NSA origin, given the open source world, did that cause any, hesitation or controversy when Red Hat picked it up? Trust issues, maybe?
Oh, absolutely. There was definitely some debate early on, concerns about, backdoors or trust. But the crucial thing is SELinux is open source.
Right. The code is out there.
Exactly. The policies, everything, it's all auditable. So for most businesses and enterprises, the massive security advantages, that ability to enforce policy system-wide, kind of outweigh those initial philosophical worries. It's just too powerful a tool.
Okay. So let's talk about why it's so powerful. What's the core problem it solves? We mentioned discretionary access control, DAC user identity, file ownership. What's the weakness there?
Well, the fundamental weakness of DA is that it kind of assumes processes are trustworthy once they're running under a certain user. The big failure point is this. Imagine a web server, like Apache or Nix. If an attacker finds a vulnerability and compromises that web server process, they instantly get all the permissions of the user that web server is running as.
Ah, right.
So if that user account can say read, etc. shadow, or browse through user home directories, you've basically lost the whole system, haven't you?
Yeah, the attacker breaks that one service, and suddenly they have broad access. DA doesn't really contain the damage.
Precisely. There's no internal containment. And that's where SELinux, using mandatory access control, completely changes the picture. It uses this core mechanism called type enforcement.
Type enforcement, okay.
This is where the idea of a security domain comes in. SELinux basically puts every single process, even if it's running as the all-powerful root user.
Even root.
Even root. It confines it to a very strict, very limited security domain. And that domain is defined by the overall SELinux system policy.
And the policy says?
The policy dictates exactly what files that process type is allowed to touch, what network ports it can bind to, which other processes it can signal, and so on. It's incredibly granular.
So back to our hacked web server example.
Right, so the attacker compromises Apache. But, Apache is running in the HTTP security type domain. The SELinux policy, enforced by the kernel through type enforcement, says, nope, HTTP is not allowed to read, etc. shadow. Or, nope, HTTP can't write to home.
So it's trapped.
It's trapped. The exploit might succeed, but the compromised process is stuck inside its designated sandbox. It massively limits the blast radius of any attack.
Okay, that's a powerful concept. It's like ultimate sandboxing for everything.
It really is. And this leads to that critical mindset shift you need, especially for the RHCSA exam.
Right, the mindset.
You have to start thinking, when something breaks, when a service fails, when an operation gets denied, your first assumption shouldn't be SELinux is broken. It should be, SELinux is correctly enforcing the policy, and I've misconfigured something.
That's a huge shift, because the temptation is just to blame SELinux and turn it off, which you mentioned is a big mistake, especially on the exam.
Oh, absolutely the worst mistake. Just running set-enforce 0 and leaving it that way, or disabling it in the config file, that's usually an automatic fail for that objective.
Why? Because the point is to manage it, not disable it.
Exactly. The exam tests your ability to manage a secure system, and SELinux is a core part of that security. You need to prove you can work with it. The default assumption has to be, SELinux is right. My configuration needs fixing.
Okay, so if we accept SELinux is working correctly, how do we use it as that diagnostic tool you mentioned?
This is where permissive mode comes in, but used strategically, temporarily.
Set-enforce 0, right. But you just said not to do that.
Right, not permanently, but temporarily it's invaluable for diagnosis. You run set-enforce 0. Now, SELinux stops blocking actions.
No. Okay.
But crucially, it still logs any denials that would have happened if it were enforcing.
I see. So you can say, try to start your service. It might actually work now, but the audit log will tell you exactly what policy rule it violated.
Precisely. You get clean, unambiguous evidence in the log about what needs fixing, maybe a file context, maybe a Boolean. You then apply the correct fix, and then, importantly, you switch back to enforcing mode with set-enforce 1.
That makes so much sense. You get the diagnostic info without fighting a broken service the whole time.
Exactly. And, let's be real. Getting comfortable with this, it only comes from practice. Hands-on, repetitive practice.
Like what? Setting up deliberate problems.
Absolutely. Set up a web server, but configure it to serve files from, say, sarvmyweb instead of rway2bml. It will fail because of SELinux context. Then go through the steps to fix it properly.
Or change the SSH port.
Yeah, change SSH to listen on port 2222. It won't work until you tell the SELinux policy about that new port. You have to build that muscle memory for the core commands, especially under pressure.
Okay, let's get into those core commands. You said there are 4 main competency areas we absolutely need to nail for the RHCSA.
Yep, 4 non-negotiables. If you master these, you can handle most SELinux tasks on the exam.
All right, Area 1.
Area 1, managing SELinux modes. Super basic, but essential. You need to instantly check the current mode. Get enforce. That tells you if it's enforcing or permissive right now.
Okay.
You need the temporary switch. Set-enforce 1 puts it into enforcing, set-enforce 0 into permissive. Just for the current session, remember.
Right, temporary. And for permanent changes.
That's editing the configuration file, etc. SELinux config. That's where you set the default mode for boot up, or where you disable it entirely if, for some strange reason, an exam task explicitly told you to.
Yeah.
But usually you're setting it to enforcing.
Got it. Check. Temporary switch, permanent config file. What's Area 2? This seems like the big one.
Area 2. Managing file security contexts. This causes, I'd say, the most common problems.
Why?
Because when you create files or directories in non-standard locations, like our sarvmyweb example, they often get the wrong default, the Linux label, the wrong context. SELinux then denies access because the policy doesn't allow, say, the web server type HTTPDT to access files labeled vart or default.
How do we even see these contexts?
The command ls-z. The -z flag shows the SELinux context for each file or directory.
ls-z. Okay, so how do we fix a wrong context permanently?
It's a critical 2-step process. You absolutely must do both.
2 steps. Step 1.
Step 1. Define the correct policy rule using semantic fif context. So you'd use semantic fif context, DHTTPD's contents, SRV Maskell. This tells the SELinux policy database, hey, files under standard FBPOB should have the HTTPD says context.
Okay, so semantic f context defines the rule, the intention.
Exactly. It makes the rule persistent in the policy. Step 2. Apply that rule to the actual files on disk using restorecon. You'd run like restorecon-rv srvmyweb. This command reads the policy definitions, including the one you just added, and fixes the labels on the files themselves.
Semantic s context to define, restorecon to apply. Got it. Now, you mentioned a pitfall here. People sometimes use tracon. Why is that bad?
Ah, yes. Tracon. It seems like it works because it changes the context on the file right now. You run tracon, you run ls-z, the context looks right, maybe the service starts.
So what's the problem?
The problem is tracon is temporary. It doesn't update that underlying policy database we talked about with Samajich. So what happens if this system automatically relabels the file system? This can happen during certain updates, or if you boot into recovery, or sometimes just by switching modes. The system goes back to the persistent rules defined by Sanage, sees your isrvmyweb directory, sees no permanent rule for it, and resets its context back to the default.
And your fix just vanished.
Poof.
Yeah.
Gone. All that Seracon work is wiped out. That's why you must use the semanage fcontext and restorecon combo for any persistent changes, especially for non-standard paths. Restorecon is really only useful for very temporary testing, if at all.
Okay, crystal clear. Semanage fcontext plus restorecon. Avoid relying on sharecon. What's competency area 3?
Area 3, managing SELinux booleans. These are much simpler conceptually. Think of them as on-off switches built into the policy.
So switches for what?
For specific permissions or capabilities. For example, there might be a boolean like HTTPD can network connect that controls whether the web server process, JCTPDT, is allowed to make outgoing network connections, maybe to talk to a database server. By default, it might be off.
Okay, so predefined exceptions you can toggle. How do we see them?
Gets bool A lists all the available booleans and their current state, on or off.
Gets bool A, and changing one permanently.
Sets bool B P. The bool P is crucial for persistence across reboots. So sets bool B HTTPD can network connect on. Without the bool P, the change is only temporary for the current session.
Got it. Sets bool -P boolean name on or off. Straightforward enough. Area 4.
Area 4, managing SELinux ports. Similar to file contexts, SELinux policy also restricts which network ports specific service types can bind to.
Like
STT typically only allows binding to the port type, which usually just includes port 22. So if you edit your shut-config to listen on, say, port 2222,
it'll fail to start even if the firewall is open.
Correct. SELinux will block it from binding. You need to tell the policy that port 2222 is now also an allowed SSH port.
And the tool for that is?
Semanage port. You'd use something like semanage port, annotation port, NIP, TCP 2222. This adds TCP port 2222 to the list of ports defined by the port type. Then SSHD will be allowed to bind to it.
Okay, semanage port to adjust allowed ports for a service type. So those are the 4 pillars. Modes, file context, semanage fcontext restorecon, booleans, set to million pegs, and ports, semanage port.
Nail those 4 and you're in really good shape.
All right, let's switch gears to troubleshooting. The moment arrives, you've configured a service, you try to start it, and nothing. Or it starts but fails immediately. Firewall's checked, config looks okay. What's the absolute first reflex?
Check the SELinux audit log. Every single time. It's almost always going to hold the clue if SELinux is the culprit.
And that log lives in varlogatataudit.log. But you mentioned earlier, reading that directly is not fun.
Yeah, it's messy. It's full of raw AVC denials, access vector cache denials, very low-level kernel messages. It records every attempted access, not just denials sometimes, depending on config. So it's incredibly verbose and not really human-readable. Trying to find the relevant denial in there manually can be like finding a needle in a haystack.
So we need tools to parse it. Tool number 1.
Tool 1 is Ausearch. It's designed specifically to query the audit logs. You typically use it with options like -m AVC to filter for SELinux denials and ASTS recent to only see things that happened recently. It helps cut through the noise significantly.
Okay, Ausearch to filter the raw log. But wasn't there another tool, the one that felt like a cheat code?
Ah, yes. Wow. The real lifesaver, Sealer.
Sealer.
It comes from the setroubleshoot-server package. Make sure that's installed in your practice systems, and it usually is on example systems. What Sealer does is actively scan the audit log for those AVC denial.
And translates them.
Exactly. It translates the cryptic AVC messages into human-readable descriptions of the problem. And even better, it often suggests the exact command or commands needed to fix it.
Seriously, like it'll tell you the semanage fcontext or setspool command?
Often, yes. I remember pulling my hair out once over a web server issue. I knew the context seemed right, ran Sealer as a varlogatataudit.log, and boom, it said, you need to run setcbool-p this boolean on. Problem solved instantly. It's fantastic.
Wow. But the goal isn't just to blindly copy-paste the command it gives you, right?
No, definitely not. The real skill is using the Sealer output to understand the nature of the denial. Is it suggesting a file context change? Then you know you need to manage fcontext and restorecon. Is it suggesting a boolean? Then it sets bool-p. Is it something else entirely?
So Sealer helps you diagnose why the denial happened and choose the right tool from our 4 core areas.
Precisely. That shows true understanding, not just following instructions. It's about connecting the denial to the correct management command.
This has been incredibly clarifying. It really paints SELinux not as this monolithic monster, but as a predictable system with specific rules and specific tools to manage those rules. Mastering it really is about demonstrating control, showing you can manage that MC layer effectively.
Absolutely. It proves you can handle a genuinely secure Red Hat environment.
Yeah.
And again, that proficiency comes down to practice. Deliberately break things, then fix them using those core tools. Semanage f context, restore con, sets bool-p, semanage port. That's the path.
Excellent. Well, before we wrap up, let's leave our listeners with a final thought to chew on.
Okay.
We've talked about how SELinux, through type enforcement, can confine even a compromised root process if it tries to step outside its defined security domain. So thinking about that power, how profoundly should that capability change the way you design system security overall? How different is it from just relying on standard user and group permissions? Where else could that principle of strict process confinement be applied in your infrastructure?
Yeah. That's a deep one. Thinking beyond just fixing denials to actually designing with confinement in mind from the start. Good food for thought.